Welcome to Brain Vision.
We're now asked to go back and look at problems 43 and 44, in which we had a beam with a distributed load on each end and then a point load in the middle that was some constant times the total distributed load acting on one of these sides. So in the first case, we told that P was W times A, where this region here had a length A, and the magnitude of the distributed load was W, which would have units of force per length. And in the second case, we were said that we were had a value of a point load of 3 WA. And so if we look back at those problems here, let's see here, we can see the one case we had this kind of distribution, and then the other case we had this distribution. So we can look at what we get for the as we vary that constant. So if we plot that as for a bunch of values of that constant, so P is now equal to KWA, so we plot that for a bunch of values of K. So here we have 0, and here we have 3. These were the kind of the extreme cases. This is where we have 1, as what we had before. And so each of these is 1/4 of K. So we can kind of get an idea of what's going on here. Is that somewhere in this region here, a little bit over 1, we will have where the minimum and the maximum are equal. And what we can find is, what we see is that this minimum always occurs in the central region where there's just a point load acting. So we really only need to look at the function that describes the moment in that region, and that function is given here. So you can derive that, and it's 1/8 times quantity 4 minus 8x over a plus 2 plus k times x squared over a squared. And so we can find this will have a minimum value if k is large enough, or it would always have a minimum value. It could be here, 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 here. And so what we find is that the minimum value occurs at when when x over a equals 4 over 2 plus k. So so when k is 0, the minimum value occurs at 2, which is here, and so it drifts over this way as we get larger and larger k's. And obviously, in fact, it gets below 1, so we'd actually have to start looking in the other region, but we're not caring about. We know that k is going to be greater than 1. K is going to be this value is going to be greater than 1, where we do have a minimum in the region from 1 to 3. And so if we plug x over a equals 4 over 2 plus k, we find that the minimum value is k minus 2 all over 2 times 2 plus k. So let's see here. When k is 0, we have minus 1/2, which is right here. That's right. And so we can see that this value will decrease as k increases. Let's see here. Then we know that the maximum will occur if when it's positive, we're at the center point, so at the L over 2, or at x over x x over a equals 2. So we can plug that into here, and we find that that is minus 1/2, or sorry, is 1/2 k minus 1. So let's see here, that value is only, let's see, when k is greater than 1, it's going to be positive. When it's less than 1, it's going to be negative. And again, we can see that when k is 0, it is minus 1/2. So what we need to do is set the negative of this value, which is the minimum, so one of these points in here, to this value. And we do that, we set this minus this to this, and solve for k. We find that k equals square root of 5 minus 1, or 1.24. And so, you know, this is 1, and this is 1.25, so it's very close to this curve here, this kind of brown one. And the peak, the maximum bending moment, or maximum magnitude of bending moment, is then square root of 5 over 2 minus 1. Again, we can plug that into here. Or that's 0.118 a squared times w.